So we already studied about the diffraction of white light and grating equation. So in this video we will be specifically discussing about the dispersive power, the Rayleigh criterion and the resolving power of grating. So the dispersive power is the change of the angle of diffraction corresponding to the unit change in the wavelength. Okay, that is we have the grating equation which is sin theta is equal to capital N small n lambda, where theta is the angle of diffraction, capital N is the number of lines, small letter n is the order of the spectrum, and lambda is the wavelength. Okay, so the dispersive power is telling us about the change in the angle of diffraction corresponding to the change in the wavelength. Okay, so this is our equation. This is equation number 1. I'm differentiating the equation number 1. What will I get? I'll get cos theta d theta is equal to capital N is a constant, order is a constant, d lambda. That is, okay. So we will get cos theta d theta is equal to capital N small n lambda. Let's rearrange this equation. So the dispersive power is the change in the angle of diffraction corresponding to the change in the wavelength. So d theta divided by d lambda, which is equal to, taking this d lambda to this side, so we will get d theta by d lambda is equal to capital N small n divided by cos theta. Okay, that is d theta by d lambda is equal to capital N small n divided by cos theta. This is the equation for the dispersive power. That is d theta by d lambda, dispersive power is equal to d theta divided by d lambda. That is change in the angle of diffraction corresponding to the change in the wavelength. D theta by d lambda is equal to nn by cos. Next thing is the Rayleigh criterion. Okay, so we already discussed about the diffraction of the white light, and we learned that for 7 different colors we have 7 different wavelengths, and these 7 different colors will be diffracted in 7 different angles. Okay, that's we already studied. So the Rayleigh criterion, which is explaining or which is actually describing how to get a perfectly separated spectral line. What is the condition for a perfect spectral line? So in the case of VIBGYOR, how to see or how to resolve these 7 different colors. Okay, so according to Rayleigh criterion, suppose I'm taking these 2 colors. One is yellow and the other one is orange, which is represented here. This is lambda yellow, which is corresponding to the spectral line of yellow, and this is corresponding to orange. So when we are doing this, while doing the experiment, we will get a yellow spectral line and we will get an orange spectral line. The principal maximum of the yellow spectral line is mentioned here, and the principal maximum of the orange spectral line is mentioned here. Okay, so in order to see these 2 spectral lines separately, the spectrum should be a just resolved or well resolved spectrum. Okay, so in order to get these 2 spectral lines separately, the spectrum should be a well resolved spectrum. So what is the condition for that resolve? What is the condition for that perfect spectral lines? When the central maximum of the first spectral line fall on the first secondary minimum, the central maximum of yellow fall on the first minimum of the orange. That is when the central maximum of the first spectral line fall on the secondary minimum of the first secondary minimum of the other spectral line of the same order. Okay, the yellow is order 1 and orange is also order 1. If both are of the same order, when the central maximum of the yellow fall on the first order minimum of the orange, then it is said to be a just resolved spectrum. If these 2 yellow and orange is satisfying this particular condition known as the Rayleigh criterion, then we can observe the 2 spectral lines separately. Okay, that is the Rayleigh criterion is explaining when the central maximum of this first spectral line fall on the first minimum of the other spectral line in the same order, that is very important, the same order, then the 2 spectral lines are said to be just resolved. And this condition is known as the Rayleigh criterion for the limit of resolution. Okay, if and only if the spectral lines are satisfying this particular condition, then we can see it separately. All the spectral lines, that is violet, indigo, blue, green, orange, yellow, orange, red, should satisfy this condition. If this is not satisfy this condition, we cannot observe these individual spectral lines. Okay, instead of the individual spectral lines, what we see, instead of this individual spectral line, what we see will be something like this. That will be the yellow and orange will be combined together and we will get a blurred image. Okay, that is an unresolved spectral line. So in order to get a well-resolved spectrum, the principal maxima of the first spectral line should fall on the first minima of the other spectral line. See, this condition is known as the Rayleigh criterion of limit of resolution. And the last topic is the resolving power. Okay, so the resolving power, which is how resolved the spectral lines are, or how beautifully the individual 7 different colors are seen. That is actually the explanation of the resolving power, or mathematically we can say the resolving power is defined as the ratio of wavelength of spectral line to the difference between the wavelength of the line and its neighboring. That is, here the wavelength of yellow is lambda 1, lambda, and the wavelength of orange, wavelength of the yellow is always less than the wavelength of orange. So I can write, suppose wavelength of yellow is lambda, then the wavelength of orange will be lambda plus d lambda. Okay, so there will be a d lambda difference between the orange, yellow and the orange. Orange will be always greater than the yellow. Okay, so in this case you can see the neighboring spectral line, yellow and orange are neighboring spectral line. I am taking this as my first spectral line and its neighbor is this orange. So the difference between the yellow and orange is represented as d lambda. Okay, so the resolving power, which is actually the ratio of the wavelength to the difference, that is lambda by d lambda. Okay, so the resolving power is the ratio of lambda to the difference, that is d lambda, which is given by the resolving power is lambda by d lambda, which is equal to capital N small n. That is, the resolving power of a grating is given by lambda divided by d lambda, which is equal to the product of the order of the spectral line and the number of lines. Okay, lambda by d lambda is the equal to n, where n is the number of lines and small letter n is the order of the spectral line. Okay, that's all about the resolving power. Thank you.